Okay, hi, welcome back. This is Calculus 1, and today we want to work with area. Let's make sure my audio is working. So we saw in the last section the indefinite integral, which we think of as that as just the antiderivative, right? So we know how to take a derivative, and the antiderivative is this integral thing. But what is the integral does it have any other interpretations? And it does, and it turns out its area is kind of the spiel that will come out of it. So let's start out just by figuring out the area underneath a curve, which is what we're going to be using this antiderivative for, believe it or not. So basically the area of a plane region and the xy plane, basically what that means. So let's look at one of the examples from the book. We're trying to find the area underneath f of x equals 2x plus 5 from the point 0 to the point 2. Okay, let me expand this a little bit. So first off, let's draw a picture of the thing, and we can kind of see what we're dealing with. I'm going to go by 1/2, so 1/2, 1, 2/2, 2, and then on the y-axis here, I'll go by 1s all the way up to, I think we need to go to 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so at 0, I'm evaluating this function. 0, we have 5. 1, 2, 3. Maybe I should put it in a different color, right? Let's put it in blue. 1, 2, 3, 4, 5. At 1/2, it'll be 6. At 1, it'll be 7. So it's just going up by 1 every time. And then 8. So I should do my tick marks a little better. And then finally, it'll go up to 9. Okay. So we want to find the area underneath that curve. And we could do this geometrically. Obviously, you could find the area. There's kind of a rectangle in there and then a triangle. And that works for problems like this. But the issue for our ancestors was finding the area under things like parabolas. And in those cases, I mean, if you want to find the area underneath this curve from 0 to 2, to find that area, sure, you could maybe do like figure out the area of this rectangle. So you use areas, you use geometric objects such that the area is familiar. We know how to find the area of a rectangle. Okay, and then maybe a long time ago they would start trying to use maybe like little triangles up here, but they could never get it perfect, you know. And it turns out that this antiderivative thing is going to get the job done for us. And it's kind of it's not clear maybe right now how that antiderivative and the area is connected, but we're gonna get there, and it takes a little bit of work. Okay. So again, back to finding the area of this plane region. What we want to do at this point is just kind of the standard way of doing it is to cut it up in a bunch of little rectangles. Okay. In particular, we're going to just use 4 rectangles for this example. And the standard way of doing this is to put the base of the rectangle on the x-axis and use the function for the height of the rectangle. Okay, and the standard way, there's two kind of standard ways we'll learn, maybe 3: right-hand endpoints, left-hand endpoints, and midpoints. Left endpoint, sorry, means that we're using the left end of the interval. So you know, this is 1/2, 1, 3/2, and then 2. We're using this point as the height of your rectangle. So our first rectangle, maybe put it in a different color, red. Come on, give me red. Would be right here. So see how I use the left side for the height of the rectangle. And then the next rectangle we can put right here. The next one, we'll use that right here, and then the next one is right here. So that would be the left endpoint kind of method. And in this case, to find the area, all you have to do is take the base and multiply it by the height. So using the left endpoints, the area underneath this curve will be approximately f of 0, using the left endpoint 0 here for your height, times the length of the base, which is 1/2. Base times height, right? Okay, and then plus f of, we used then 1/2 for the base, for the height. Okay, so f of 1/2 would be the height there, times the base is 1/2, plus f of 1, so that would be this point, times 1/2 plus f of 3/2 times 1/2. And then if you evaluate that, f of 0 is 5. We could factor out the 1/2 from everything, plus I guess 6 plus 7 plus 8 times the 1/2, and what would that be? 15, 26, so 13 approximately for the area. Okay, so you could also use right endpoints then. So let's do the right endpoints in yellow. So for the right endpoints, we'll start with, okay, so area is approximately, the area underneath the curve is the sum of these rectangles, and now the rectangles, the heights will be given by the right endpoint. So we'll start with 1/2 to give us that first rectangle, and then 1 will give us the height of the second rectangle, and then 3/2 will give you the height of the third, and then 2 will give you the height of the fourth rectangle. Okay, so it'll be f of 1/2 times 1/2 plus f of 1 times 1/2 plus f of 3/2 times 1/2 plus f of 2 times 1/2. And again, you can factor out the 1/2, and you'll have 6 plus 7 plus 8 plus 9, and that'll equal 13, 22, 40. I think that's 15. Okay. Right. So we want to make this more mechanical. The ultimate goal here is to fill it up with an infinite number of rectangles. And to do that, what we're going to do is kind of just put a whole bunch of rectangles in there and let the number of rectangles go to infinity. So we'll say we're going to put n rectangles in there, let n go to infinity, and that should be the answer. Okay, so if the more rectangles you use, hypothetically, the better your approximation will be to the area underneath the curve. So right now you can see the right endpoint method is including the area, this area, which actually isn't even underneath the curve, right? So there's going to be some error there. And then the left endpoint is actually including area, or not including area that it should, right? There's these little wedges that it's not including. So the way around it is to just increase the number of rectangles to infinity. Okay. You may have seen the same idea when you're trying to figure out the area of a circle using triangles. So I don't know if anybody ever showed you that, but you can approximate the area of a circle using triangles. So first you could use like 4 triangles, but you see that's not going to be a very good approximation because you're missing a whole bunch. Okay. And so what do? So then you can make a better approximation by using, I don't know, 8 triangles, right? So you let the number of triangles go to infinity, and that's kind of the process we're going to be using here. So in the beginning, right now, we're going to be working with just using a number like n, or sorry, like a number like 5 or 6 rectangles, and then eventually we'll take the limit as n goes to infinity. So, okay, the hard part is kind of this part right here, these sums is what they call it. And the way to deal with these sums is to kind of develop some notation. Okay, so we're going to have kind of a mechanical way of presenting this summation and putting it into variable form where we can take the limit of it as the number of rectangles goes to infinity. Okay, so right, we're going to need a couple of things to do this, right? We're going to need summation notation, which you may or may not have seen, so I'm going to have to introduce that. We need a formula that can generate the left endpoints and the right endpoints. So in our formula, I need a formula that can generate 0, 1/2, 1, 3/2, and then also over here, 1/2, 1, 3/2, 2, for any given circumstance, right? Okay, so I don't know how to proceed. Let's take this up a notch and try the same problem, but with 8 rectangles, okay? Okay, so the same example. So f of x, and you can use any curve you want. Let's try, I don't know, 2x plus 1, right? Just try to find the area underneath that thing. And you don't even have to use, you know, we can do like the ancients did and try maybe even a parabola. Okay, so x squared, and we want to know the area going from 0 to x squared plus 1. Let's move it up a little. We want to know the area going from 0 to 2, and we want to use, I don't know, 8 rectangles. Okay. Okay. Don't necessarily need a picture, but you can draw it if you want. X squared plus 1 is shifted up 1. So going by ones, here's 2, and then at 2, 1, 2, 3, 4, 5, apparently. Here's our parabola. I need to figure out the area underneath this curve in here. Right, and first things first, I need to kind of chop up the number line into 8 rectangles. Right? So, you know, what do I go by? Do I go by halves, thirds? Well, it turns out there's a formula for it. In general, the widths of those rectangles we're going to call change in x, and the formula is always b minus a all over 2. Okay? So in this particular case, change in x will be, and what is b, what is a, right? This is a, this is b, and it should be all over n, sorry, not 2. That should be an n, where n is the number of rectangles. Okay. So in our case, it's 2 minus 0 all over 8. So we'll get 2/8. In other words, we're going by 1/4. Okay. So 1/4, 2/4, 3/4, 4/4, 5, 6, 7, and then 8/4. Okay. Okay. So for our rectangles, if we're using the left end points, we can put those in red again. We're kind of going to have these guys, right? Because we're using the left point as the heights. Doing my best to draw this guy. Okay. And I would really like a formula to give me these points on the number line. I don't have to guess at it. And what are the, whoops, and I don't need that last point. The left end points are not including that last point, which I just drew. And I accidentally erased everything. Right, so I need a formula such that when I go to find the area using the left end points, I'll say a sub L, what am I doing here? I'm going f of something plus f of something, and of course we have the 1/4 times everything, plus f of something times 1/4 all the way up to the 8th one, f of something times 1/4. I need a formula that can generate what goes in here, right? We know what goes in there. It's going to be 0, 1/4, 2/4, 3/4, 4/4, 5/4, 6, okay, etc. How do I get that formula? Well, that formula is an arithmetic sequence, okay? It's based off an arithmetic sequence. And we have formulas for arithmetic sequences, okay? You may remember that from pre-calculus if you got that far, right? So our formula will be a sub I equals a sub 1, the first endpoint, plus I minus 1 times the difference between the endpoints, which we're using as change in x. So you may have seen this formula with a d in there instead of change in x. Okay. So in particular, our formula for these little endpoints, these left endpoints, will be a sub I, or a sub 1, sorry. A sub 1 in our case is just 0, plus I minus 1 times change in x, which in our case is 1/4. Okay. So I think that'll do it, right? That's just, we can rewrite it as I minus 1 all over 4. Okay. And let's see if it works. So a sub 1 is going to be 1 minus 1 all over 4, which is 0. And sure enough, that's that guy right there. A sub 2 is going to be 2 minus 1 all over 4, which is 1/4. Seems to work, right? A sub 3 is going to be 3 minus 1 all over 4, which is 2 all over 4, which is 1/2. It works. And then all the way up to a sub 8. So we should be getting, at a sub 8, we should be getting this guy right here, okay, which would be 7/4. Okay, if we did things right, a sub 8 should be 7/4. So does it work? Well, let's put it in there. I is 8, so 8 minus 1 all over 4, and yeah, 7/4. Okay. So it works. We have this little formula which kind of generates those those characters. All right, we need another formula for the right endpoints, right? So a sub r, again, we have these f of somethings. We should start with f of 1/4, and then of course go all the way up to, I need to put a 1/4 in here, f of something times 1/4, where this something this time should be 2. Okay. Okay, so our formula this time, a sub I, will equal a sub 1, and then we're going to just start a little bit over, right? So we'll start with by adding in plus change in x. So effectively what it does is just change a sub 1, the starting place, into a sub 2. Okay? And then plus the I minus 1 times change in x. Okay? So in our case, a sub I will be a sub 1, which is now 1/4, because we're not starting with the left endpoint, we're starting with the right endpoint. So if you look back above at the picture in blue, this is where I want to start now. Okay? And that will give me rectangles where the tops are determined by the right endpoint. Okay? So if I were crazy enough to go through and redraw all of those, it would start to look something like that. I'm not going to go through and do that because I'm not crazy. Then plus change in x, would be 1/4, and then plus I minus 1 times our change in x, which is again 1/4. Okay, let's clean this up. 1/4 plus 1/4 plus 1/4 I minus 1/4, so I just distribute. And that will be, these cancel, and we're just going to get 1/4 I plus 1/4, okay? Which is the same as I plus 1 over 4 if you wish. But let's write it the way we had it. Whoops, a sub 1 is 0, so I did make a mistake there. Ugh. So the first one is 0, but then, I mean, technically you just put 1/4 there. Okay, sorry. This is all going so well, and then I had to screw it up. I apologize. So anyways, yeah, to start at the next point, all you do is add the change in x into a sub 1, and effectively you get a sub 2 as your new starting place. Okay. Right. So what is this then? It'll be 1/4 I. Okay, and let's see if that works, right? So a sub 1, if I plug in 1 for I get 1/4. So this guy should be 1/4. Sorry, phone's ringing. I'm expecting an important call. Anyways, let's see. So the first one, a sub 1 is 1/4, and then a sub 2 should be 2/4. Okay, so a sub 2. So we get, if you put in 2 for I, you'll get 2/4. A sub 3 is 3/4. Okay, so it looks like it's working, right? And then a sub 8 should be 2. So you put in 8 for I times 1/4 will be 8/4, and certainly it works. Okay. So it seems we have a formula then. You gotta be a little careful with a sub 1, I guess. It seems we have a formula where that will produce these numbers. Okay, so in general, you could basically say, okay, what if I had, you know, n rectangles or whatever? You could put it in general terms. You could put it in variable terms, and then we're going to be able to take a limit of it, and things will be nice. Okay, so to condense this even more, now that we have this formula, what we're going to do is use summation notation. Right, so for something like a sub r, the right-hand endpoints, what we'll end up doing is rewriting it as a sum of f of, and then we want this 1/4 I formula to produce these points times change in x, and we'll go from I equals 1 to, in this case, we have 8. Okay, so that's what we're going after. And, you know, this summation formula is maybe something you've not seen before, but it's just a shorthand way of writing out this big, long sum, okay? And we could write it out right now. So you know, what is this? This is the sum from I equals 1 to 8 of f of 1/4 I. Change in x we said was 1/4. Right, and basically what this thing means is that first you're going to put in I equals 1 into this formula, so you get f of 1/4 times 1 times 1/4. So it's this thing, and you're plugging these values in what they call the lower limit here, going from 1 to 8. Okay, so first you plug in I equals 1, then you plug in I equals 2, and you'll have f of 2 times 1/4, which will be 2/4, times 1/4, and then you know, I is 3, so plus f of 3/4 times 1/4, and you keep on going, dot, 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 all the way up to I equals 8. And right there, that'll be f of 8/4, which of course is 2, times 1/4. And what we have there then is a compact way of dealing with these big, ugly sums. Okay. Okay, so in order to handle this a little more effectively, what I need to do then is just to talk about sigma notation. If you've not seen that before, usually if you take a class like discrete math, they'll beat this into your head pretty effectively. But you know, a lot of us have not taken that. So let's take a look. So in general, you're going to have some formula And you may notice in all this stuff up here, I'm using this a sub I thing like a formula, but really it's like an f of I, right? It's like a function of I. And all you're doing is plugging in, like in this case, this would be down here, f of 1. It's just a different way of writing our usual function notation. It's just that because we're dealing with sequences, we have this funny way of writing it. So this thing right here is basically just some formula in terms of I, and you're plugging these I variables, the I going from 1 to n into it, and then you're adding up each part. Okay, so first you try I equals 1. If you plug 1 in for I, you get a sub 1. And then you plug in I equals 2, you get a sub 2, and then you go all the way up to the one before, n is n minus 1, of course, and then plus a sub n. Okay. So the book should give you some easy examples to kind of just expand and get used to the idea. So k goes from 0 to 4, 1 all over k squared plus 1. And computer programming, you see this a lot. You have a lot of work with summations. Okay. So first I put in k as 0, so I'll have 1 all over 0 squared plus 1 is 1. Plus, so this was k. And you can kind of note below which term you're on if you're worried. K equals 1. I have 1 squared plus 1, which is 2. K equals 2, so I'm just plugging these k values into this k formula, this a sub k formula. Okay, so k equals 2 is 4, 2 squared is 4, plus 1 is 5, plus 1 all over, so now I'm at 3. 9 is 10, plus the final one, k equals 4. 1 all over 16 plus 1 is 17. And then you could add those up if you were ambitious enough to do so. Okay. There's going to be some ones that kind of you need to know. For example, going from k equals 1 to 5 of 1. Okay. What do you think that's going to be? You need to take a wild guess. And so k equals 1 is 1, plus k equals 2, you get 1, and then you go all the way up to 5, right? This is 3, 4, 5, so 1, 2, 3, 4, 5, you get 5. So it turns out in general, and you would have to prove this via induction, but in general, we have the formula, the sum. Let me use a different index, or different, index. They call that I thing an index. So I, from 1 to just some variable n of 1, is always going to just equal whatever that upper limit is, n. Okay, so it just equals n. Also then, so this is like the first one we kind of want to know. Also, if you have c, if you're adding up some number like c from 1 to n, for example, if you're adding up 3 from I equals 1 to 4, right? You get 3 plus 3 plus 3 plus 3. What does that equal? Well, that's just 3 times 1 plus 1 plus 1 plus 1. In other words, it's 3 times 4. Okay, so it's just 3 times this upper limit. Okay, so in this case, it's going to be c times n. There's some other formulas that come up in our work with summations that we want to be familiar with. This guy right here, I equals 1 to n of I, is equal to n times n plus 1 over 2. Another one, the sum from I equals 1 to n of I squared is going to be n times n plus 1 times 2n plus 1 all over 6. And then finally, the sum of I cubed from I equals 1 to n. This one, weirdly enough, is just a square of 3. So it'll be n squared times n plus 1 squared over 4. Okay. Okay, I'm not going to force you to memorize these. I probably should, but I'm not going to force you to. Okay, some other factoids that we should know also, in addition to these, the sum, if you have a finite sum, and later on we'll deal with infinite sums in Calc 2, but if you're dealing with a finite sum, for example, I equals 1 to n of k times some formula, a sub I, you can actually factor the k out, okay? Equals 1 to n of a sub I. And that makes sense because all this thing is a big, huge sum. Each one is going to have a factor of k, and you can factor that common factor out of the sum. Okay. Also, if you have a sum of a difference or a sum, so say a sub I plus or minus b sub I, just like with integrals, you could split this up. Okay, so it's a sum of I equals 1 to n of a sub I plus or minus the sum from I equals 1 to n of b sub I. Okay, great. So let's look at an example where we have to kind of apply all of this junk to evaluate a sum. So here we have I equals 1 to 20 of I minus 1 to the second power. Okay, so what you don't want to do is literally write out all 20 terms and then add them. Okay, you don't want to do that. So what do I do instead? So instead, I'm going to first FOIL that thing out. So I'll have I squared minus 2I plus 1. And I'm going from I equals 1 to 20. And then I'm going to split that thing into 3 sums. So I'll have the sum of I squared, and I'm going to factor out the negative 2 from the second sum. So negative 2 sum of I, and then plus the sum of 1. And of course, the limits on the sum are all the same. So the I equals 1 to 20, that's all there still. I'll go ahead and write it. And then I use these formulas up here to rewrite those sums. Okay, so the first one, I need the formula for I squared. That is, you know, even I have to look back. I never use these, I guess. So just as to remember, it's n times n plus 1 times 2n plus 1 all over 6. Okay, and all you're doing is plugging in this top guy for n. Okay, so it's 20, let me go back to light. It's 20 times 21 times 41 all over 6. And then minus 2 times, and then we need the formula for the sum of I, which was n times n plus 1 over 2. So again, you're plugging 20 into that formula. So we have 20 times 21 all over 2. And then finally, plus the formula for the sum of 1 is just n. So it's this upper limit here, 20. So plus 20. Okay. And then we could evaluate that. I'm getting 2470 as my answer. Okay. Okay. So now we want to apply this to finding areas underneath curves. Okay, so we can kind of go back to this example here, and instead of using 8 rectangles, I'm going to use n rectangles, and then let the number of rectangles go to infinity. And what I'm hoping is I'll get the actual area underneath the curve. It might be better to first start with this example here, the first example, f of x equals 2x plus 5 from 0 to 2 with n general rectangles, because we can actually find the area of that thing, right? So going back then to that example, we have f of x equals 2x plus 5. We want to know the area underneath the curve going from 0 to 2. And in this case, we're going to use n rectangles, and then let n go to infinity in order to get the actual area. Okay, so let's see if I have a definition in general about this. Okay, so yeah, there's a definition in the book. Maybe I'll just I'll squeeze it in here above. So the definition is that area underneath the curve is actually equal to the limit of the sum of the rectangles, and the limit as n goes to infinity, if you have I equals 1 to n of the heights f of, and we could use, it doesn't have to be left endpoints or right endpoints. You could use any point in the interval, so they just write c sub I, and then times change in x. And that will give you the area underneath the curve. Okay, but in general, we'll use either right-hand endpoints or left-hand endpoints. It's just, it turns out, under nice conditions, it doesn't really matter what point you use. For us humans, it's easier just to pick out left endpoints or right endpoints, and then use the formulas, like this guy right here. Okay. And then we're going to be taking the limit of it. Okay, so for the right endpoints, we had that formula, and let me borrow that and kind of going to borrow it if the computer software will let me do that. Thank you. And I'm going to bring it downstairs. Okay, it's very slowly moving. It's a review over what we've done. Let's see if I can speed it up a little bit. No, you can't. Okay. Some of our formulas. It's a concrete version. Okay, so now we want to find the area underneath this curve. Here is our right-hand endpoint formula for, wait a second, this was the wrong one. I apologize, that's not even the one we want. I frickin' copied the wrong one. Did I even do it for those? No, I didn't do it for those. Sorry. Okay, just, well, I guess I'm going to have to regenerate it, right? Okay, so for the right-hand endpoints, normally it was f of 0 plus f of, what did we go? In our case, it was like 4, so we had f of, and it's times 1/2, right? Every one of these is times 1/2. And then f of like 1/2, and then, you know, blah, blah, blah. The last one was f of 3/2 times 1/2. And then you could rewrite that as a sum of f of some formula. That's going to be one of those arithmetic formulas that we have, times our change in x, which in this case was 1/2. And the formula that we would have to use based off the endpoints, 0, 1/2, 1, and then we would have 3/2 for the other one. So there was a 2 here eventually. The formula is a sub I equals a sub 1, which is 0, plus I minus 1 times change in x, which in that case was 1/2. So it'd be I minus 1 over 2. And it would have gone from I equals 1 to 4. Okay, so we want to change this and make it more general now. Our new formula then for n rectangles, and then we want to take the limit as those numbers of rectangles goes to infinity, we would go from I equals 1 to n. Okay, so that's one thing that's different. And then we have f of some new formula times change in x. Okay, where our change in x is going to be different because it's going to be based off of n as opposed to 4, right? So now we have just general n rectangles. Okay. So first off, that change in x formula. Change in x, if you remember, is always b minus a all over n. So in our case, the endpoints are 2 and 0. So it's going to be 2 minus 0 over n. In other words, 2 over n. So at least we could rewrite the change in x part. This will be the limit as n goes to infinity of the sum from I equals 1 to n of f of something times 1 over n. And then that something. What is that something that goes in there? So I need a formula, our formula for generating these sequences, and I want the what are we doing? The left endpoint. Maybe we should do the right endpoint. The right endpoint I think is going to be easier. Okay, anyways, so this was the left endpoint above. I apologize. So yeah, I want to do the right endpoint. Point formula, because that formula turns out to be easier. You know, in general, it was a sub 1 plus change in x minus I minus 1, or actually plus I minus 1 times change in x. And if you simplify it, it's a sub 1 plus change in x plus I change in x minus change in x if you distribute, right? So it'll end up being a sub 1, these cancel, plus I change in x. And in our case, a sub 1 is really 0. So it'll just be 0 plus I change in x. In other words, I times change in x, which is 2 over n. So our formula will be 2I all over n. Okay? Okay. So that was just some extra work we had to do. Now I have to plug 2I over n into the actual function. So if you remember, the function f of x is, where are you, 2x plus 5. So wherever you see x, you're going to put 2I over n. So it's the limit as n goes to infinity of the sum from I equals 1 to n of 2 times 2I over n plus 5 times 1 over n. Okay. And then we're going to clean this up a bit by distributing, etc. So we have the limit as n goes to infinity of the sum from I equals 1 to n of 4I over n squared plus 5 all over n. And then what is this thing? This thing is one of those, like this example here. It's one of these characters. Okay? And we have to use our formulas here in order to simplify it and find a nice formula in terms of n. Okay? All of these sums are dependent, this sum is dependent on I. So if you have an n, you can factor it out of the summation. The n's become constants. Okay, that you can just factor out. Anyways, first we'll split up the summation. Okay, so we have the sum from I equals 1 to n of 4I all over n squared, and then plus the sum from I equals 1 to n of 5 over n. We can factor out then any constants, anything that's not dependent on I, you can factor out. So we'll have the limit as n goes to infinity of, I could factor out 4, I could factor out the 1 over n squared. And then I'll just have the sum of I from I equals 1 to n. And then plus, I could factor out 5, and I could factor out an n, 1 over n, and I'll be left with 1. I equals 1 to n. Okay. And then this will equal, of course, the limit as n goes to infinity of 4 all over n squared. And then I, the sum of I from 1 to n is just that n times n plus 1 over 2. And then plus 5 over n times the sum of 1 from 1 to n is just n. Okay. We could rewrite this a little bit. So I get the limit as n goes to infinity of, I guess, 4n squared plus 4n all over 2n squared. And then plus 5. Okay, so that first limit is like a chapter 4 limit. It's all you have to do is pick off the high degree terms. And usually that's what these turn into, this type of limit, where you could just look at it and know the answer. The limit of that thing will just be 4 over 2, in other words, 2. So you'll have 2 plus 5, which is 7, believe it or not. So that would be the area underneath that curve. Let's go back and actually find the area geometrically. Okay, so the area underneath this curve is just basically the area of this triangle times the area of this rectangle. Okay, so there's a rectangle here. So the area of that rectangle is base, which is 2, times height, which is 1, 2, 3, 4, 5. Oh my gosh, I can already tell it's not right. What did I do wrong? No, no. Frick. What did I do wrong? 2 over n. Two x plus 5. I'm going to actually have to pause the video to figure out my... Oh, sorry, I found it. It's the change in x. I accidentally put 1 over n here. It should be 2 over n. So this is 2 over n. This will be, or 8i over n squared, and this will be 10. This will be 8. 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 This will be 8. This will be 10. And then finally, it'll be 8 over 2 plus 10, which is 4 plus 10, which is 14. Oh, jeez, oh man. Okay, going back up here, I totally apologize. It just ruins the whole video. I'd go back and redo it, but it's just no. Okay, so anyways, back here, the rectangle's area is 2 times the base times height, which is 10. The triangle's area then, maybe put it in a different color. The triangle right here, so the area of the triangle is 1/2 base, which is 2 times height, which looks like it's going from 5 to 9. I believe it's 4, right? So, you know, yeah, 9 and then 5. Okay, so that would be one. That would be just 4, and then the sum of those two areas, of course, is 10 plus 4. So I hope that at least kind of convinces you that you can use this method to figure out the area underneath the curve. Okay, so I did that. Okay, ultimately though, you want to figure out the area underneath these. I mean, that's kind of silly to use this high-powered method for figuring out the area when you could just do it geometrically in 5 seconds. But it's these curves, these parabolas, find the area underneath a parabola, which really gave our ancestors a ton of trouble. Okay, so we want to be able to work with those. Just some other points of interest. I think we're good. The book will talk about lower and upper sums, so you could kind of see what's going on with the idea of the circles. So you could kind of bound a circle's area in between these triangles that are inside, and then you could actually put some triangles on the outside. So you can circumscribe or inscribe the circle. Okay, and what you end up doing is having a bigger than area sum and a lower than area sum. And it turns out for certain conditions, when you take the limit, these sums will end up equaling each other. Okay, and what that leads to for us is that basically you don't have to use left-hand endpoints or right-hand endpoints. You could use any point in the interval for the heights of your rectangles. And that's where in this definition for area down here, that's what that C is all about. Where did I put my definition for area? Right here. So you see there's a C sub I in here. That C sub I just means any point in the interval. So you could use anything you want. You could use left endpoint, right endpoint, midpoint, all these other things. Okay, on top of that, let me give you the basic formulas for these sums using left-hand endpoints and right-hand endpoints. So the right endpoint formula is not going to end up being the limit as n goes to infinity of the sum from I equals 1 to n of f of the a value. If you have the interval from a to b, it's going to be the a value plus I minus 1 times your change in x, which is b minus a all over n, times change in x. For the left endpoint on the interval from a to b, you have the limit as n goes to infinity of the sum from I equals 1 to n of f of, how would that work? It would be a plus change in x plus I minus 1 times change in x times change in x. But that always simplifies, and this is usually why we use the left end. Sorry, this is the right endpoint. I reversed them. I don't know my left from my right. I'm sorry. So this would be the left endpoint. This is the right endpoint version. This formula simplifies into a plus I change in x. Okay, so it's preferable to use that formula. There's also the midpoint formula. Limit as n goes to infinity of the sum from I equals 1 to n of f of a plus, and you just shift it over by changing x over 2, plus I minus 1 times change in x, and that would get the job done. Okay, let's make sure I'm on track with my notes. I think we're on track, sort of. Okay, so where to next, right? Let's look at one of these, like a parabola type version like we had up here. Let's see if we can redo that one and get a better answer. So x squared plus 1 from 0 to 2. So we have our example, f of x equals x squared plus 1 from 0 to 2. And I want to find the exact area using this limit definition for area. So I'm going to use my right endpoints formula. So I'll have limit as n goes to infinity. I need to figure out what change in x is, right? So change in x will be 2 all over a minus b all over n, so 2 over n. It'll be the sum from I equals 1 to n of f of a is 0. So this will end up just being I times change in x. It should be 2i all over n. So it's pretty much the same as the last one. It's kind of lame. Oh well. So and then times 2 over n. All right, so I need to figure this guy out. This will be the limit as n goes to infinity of the sum, and I need to plug this into here. So I'll have 4i squared all over n squared plus 1 times 2 over n. And then that'll be our limit of the sum of 8i squared all over n cubed plus 2 over n. Okay. And then I need to start splitting up the limit and junk like that. So I can factor out anything that's not dependent on I. So I can factor out the 8 all over n cubed, and then I have the sum of I squared from I equals 1 to n, plus 2 times 2 over n times the sum from I equals 1 to n of I. No, just 1, sorry. And then, what next? So I have the limit as n goes to infinity of 8 all over n cubed, and then I have a formula for I squared that goes n times n plus 1 times 2n plus 1 over 6. Right? So times n times n plus 1 times 2n plus 1 over 6. I don't know why I wrote that twice. Plus 2 over n times the sum of 1 from 1 to n is just n. Okay. Limit as n goes to infinity. All I need are the leading terms, so you could kind of figure out the leading term by cheating a little bit and just taking the first terms of each factor and multiplying those out. So you have n times n cubed. 2 times 8 is 16. N cubed all over 6n cubed. You don't need the other stuff. Plus 2. And of course that will just be 16 over 6 plus 2, which is 8 thirds plus 6 thirds, which of course is 14 thirds. Okay. Later we'll be able to figure this out in a quicker way, quicker method. If you took a little bit of calculus, you may already know how to do this. The trick turns out to be a definite integral. So the indefinite integral we would just integrate, right? We would get antiderivative x cubed over 3 plus 2x. Okay. For the definite integral, what you do is take that indefinite integral and evaluate it on these endpoints. So you evaluate it at first 1, so you get 1 all over 3 plus 2, and then evaluate it at 0, you get 0 plus 0. So we would end up with, and plus go to the 2, sorry. So that would be 8 thirds plus 2. You get 8 thirds plus 6 thirds, which is 14 thirds. And of course, that's the same answer. Okay, so eventually we'll find that there's this unique relationship between the antiderivative formula and the definite integral and finding area underneath curves. Okay, and that's kind of the punchline of Chapter 5 with the fundamental theorem of calculus, okay, which connects all this. Let's look at a midpoint problem. Okay, so using the midpoint, I'm not sure what number I'm on. I'm just going to cheat and call this number 5. Using midpoints. Okay, so for this example, let's use another parabola. F of x equals x squared plus 3. And the interval from 0 to 2 with 4 rectangles. Okay. So we'll have 1, 2, 3, some parabola going off like that, and we want to figure the area underneath it from 0 to 2. And I need to split it up into 4 rectangles, but in particular, I need the midpoints. Okay, so if you kind of extract the number line here from 0 to 2, you can split it into 4 parts, 1, 2, 3, 4, and I need to use the midpoints this time for the heights of my rectangles. Okay, so you can just use your wits about you. If this is, and then this would be 3 halves. 1 half divided by 1 half minus 0 divided by 2 is 1/4. 1 minus 1 half divided by 2 is, whoops, I want the midpoint. So 1 plus 1 half divided by 2, sorry, is 3 halves divided by 2 is 3/4. Okay, so you could go that way, but there's also, you could use those arithmetic formulas, right? So I said my formula, a sub I, was a in general, It'll just be our a value. Plus, what we're going to do is do a change in width over 2, right? So that will shift the sequence from 0 all over to 1/4. And then you're adding in this I minus 1 change in x. Okay? So in our case, a is 0. Our change in x is going to be 2 minus 0 over 4, so 1/2. So plus 1/2 divided by 2 is 1/4, plus I minus 1 times 1/2, which is 1/4, plus 1/2 I minus 1/2, so this would be 2/4. So it's going to be I over 2 minus 1/4. That seems like a lot of work. 2/4 minus 1/4. So a sub 1 should be 2/4 minus 1/4, which is 1/4. A sub 2 should be 4/4 minus 1/4, which gives you the 3/4, etc. Right? And then this one, what the heck is that? 2 plus 7/2 divided by 2, 7/4, right? It should be 7/4. So let's see if that's right. A sub 4 is 8/4 minus 1/4, which gives you the 7. Okay, so we're good there. So either way you do it is fine. I don't care. Then you have to add up your areas. So the area under the curve would be approximately f of 1/4 times our change in x plus f of 3/4 times our change in x plus f of 5/4 times our change in x plus f of 7/4 times our change in x. And if you go through that rigmarole, you'll end up with about 8.625-ish. Okay, other stuff, other weird stuff. And instead of finding area bounded by the curve and the x-axis, we can also worry about regions bounded by the y-axis. Okay, this problem's a little bit longer. You may or may not want to watch, depending on your level of disgust with what's going on. Here we have a function g of y equals 4y squared minus y cubed, and we want to go from 1 to 3. Okay. So what the heck is that thing? This is, well, let's just take a look, right? Y is 1, 2, 3. And then when y is 1, x is, so it's g of y is kind of like a formula for x. So x is 4y squared minus y cubed. So g of 1 anyways, I guess I'll do that over here, will be 4 times 1 squared minus 1 cubed. So that'll be 3. So we have a coordinate of 3, 1. 3, 1. And then the other point at 3, so g of 3, is going to be 4 times 9, which is 27, minus, oops, 4 times 9 is not 27, I apologize, that's 36, minus 3 cubed is 27, that'll be 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have the coordinate 9, 3. 3. And then the graph is doing something in between. I'll just kind of cheat a little bit and draw it like that. We want to find the area underneath that curve, like in this direction. So we want to find this area. And it's basically just the same game, except everything is kind of reversed. The rectangles we're looking at, if we want just 4 rectangles, you could use the left endpoint, which would be in this orientation right here. So our first rectangle would be here, and then our second rectangle, oops, would be like right here, and then our third rectangle would be right here, and then our fourth rectangle would be right here. Okay. We want to use the limit process to get the area underneath this curve. Okay, so we're again, I will use I always like to use the right-hand endpoint formula. So I'll be doing the limit as n goes to infinity of the sum of g of my formula times, in this case, change in y. Okay, where change in y, in this case, will be just, this is b, this is a. So 3 minus 1 all over n. So 2 over n again. And then on the inside, the formula for the little points will be a sub I equals a plus change in y times I believe. So in our case, that'll be 1 plus 2i over n. And so we'll have the limit as n goes to infinity of the sum of g of 1 plus 2i over n times change in y, which is 2 over n. Okay. And then the fun begins, right? Because this function is so kind of nasty. Let's remind ourselves here what this thing is. G of y is four y squared minus y cubed. Okay. Okay, so let's go at it. Infinity of the sum. So we're plugging this material in for y here. So we'll end up with 4 times 1 plus 2i all over n squared minus 1 plus 2i all over n cubed times 2 over n. You could factor out two factors of 1 plus 2i over n. So you have the sum of 1 plus 2i over n squared times 4 minus 1 plus 2i all over n times 2 over n. Okay. This will be the limit of the sum. I'm going to end up having to, unfortunately, FOIL like crazy. So 1 plus 2i over n squared will be 1 plus 2i over n plus 2i over n, which gives you 4i's over n, plus 4i squared over n squared, times 4 minus 1 is 3, and then minus 2i all over n, and then times 2 over n. And this will be the limit of the sum of, and now I have to multiply this part out. So 3 times all of these, and then the 2i minus over n times all of those. So you have a 3 plus 12i over n plus 12i squared over n squared minus 2i all over n minus 8i squared over n squared minus 8i cubed over n cubed. On the outside, we still have that 2 over n. And then combine some like terms, right? So we'll have 3 plus 10i over n. 12 of those minus 8 of those is plus 4i squared over n squared. And then minus 8i cubed over n cubed times 2 over n. We're getting there. Let's just make sure I'm kind of on the right track. Go ahead and distribute now. So the limit of the sum of 6 over n plus 10i, 20i all over n squared plus 8i squared over now n cubed minus 16i cubed over n to the 4th. And then we could start splitting up the sum. So this will be the limit of a sum, and I'm going to factor out the non-I parts, right? So I'll have 6 over n, sum of 1 plus 20 all over n squared. sum of I plus 8 all over n cubed times the sum of I squared minus 16 all over n to the 4th times the sum of I cubed. And then this will be the limit of 6 over n times n plus 20 all over n squared times n plus 1 all over 2, just using the formulas from above, plus 8 all over n cubed times n plus 1 times 2n plus 1 over 6. And then finally, minus 16 all over n to the 4th times n squared times n plus 1 squared all over 4. And then we could kind of start looking for the high degree terms and those nasty looking ones. 6n over n would just be 6 in that guy, plus what are the high degree terms? So to get the high degree term in the numerator, if you have a bunch of factors, you just pick off the first term in each factor and multiply them. Okay, so that will be 20n squared all over 2n squared plus, and do that trick again, right? So 8 times n times 2n is the top. So I'll have 8n squared times 2n squared. That's not 8 anymore, is it? It's 42. It's 16. So 8 times 2 is 16. Someday the pen will work. 16, and then n, we have an n cubed all over 6n cubed, and then plus, and again we play this game. We have a 16 and n squared and another n that'll be squared. So you go plus, or rather this one's minus, right? So minus 16n to the 4th all over 4n to the 4th. And then as n goes to infinity, just have 16 plus 10 plus 8/3 minus 4. So 16 minus 4 is 12. 36/3 plus 8/3 is 44/3, and that would be your answer. Okay. It's good practice, these summation notations. I know if you already took like high school calculus, the cat's out of the bag, right? You know a quick way to do these. But it's good practice because in general, in later classes, you may be expected to work a lot with summation notation. And this gives you great practice at it, and it also teaches you a little bit about the mechanics of this area problem, and what we're going to look at next, called the definite integral. Okay, so I think we'll leave it at there. Make sure you're reading the section. There's that upper and lower sums I didn't really go into very much here, but I think we did enough for the day. So I'll leave it at that, and thanks for watching, and we'll see you next time.